Okay, let's get started. So I haven't finished the grading of your exam. Most probably next Thursday or next Tuesday, I'll return your exam. But if you have a big concern of your exam, for example, you feel you did very bad, you want to discuss with me, we can talk about it. Or you feel you did so good, cannot sleep, so excited, also you can share with me. Okay, so next Thursday, next Tuesday, so I'll return, then we can talk about more about the exam. So today, let's move to next chapter. So first two chapters are basics. Okay, so in general theories about this distributional theory. Now starting from chapter 3, we will talk about some specific distributions. So you can think about this is an application of first two chapters. But they have some special issues from the chapter 3. So these distributions are the most well-known distributions in statistics. Okay. Some of them are discrete, some of them are continuous. So for discrete random variables, we can say we will mainly talk about binomial distributions. Okay. This of course includes ballooning or multinomial. Okay. Also Poisson is another discrete random variable. Okay. So these two, we'll talk about it. Now for continuous random variable, we will talk about the gamma related. For example, gamma, chi-square, beta distributions. So these are all involved a function, special function called a gamma function. We will talk about it. Okay. Now of course, the most important distribution in statistics, we will spend a lot of effort to talk about normal distributions. This includes multivariate normal distributions. Now for statistical inference, you probably know before some well-known distributions. For example, the T distributions. If you learned some fundamental statistics, this t-test, confidence intervals, they're based on T distributions. If you learned some linear regression, the F distributions. Okay. So these are the main distributions we will talk about in this chapter. Now today, let's focus on binomial. Each distribution has its own feature. If you want to learn binomial well, the first formula you should know is a plus b to the power n. If you don't know the expansion of this formula, you cannot learn binomial well. So a plus b to the n is the sum. X from 0 to n. N choose x. A to the x, b to the n minus x. This is the most important formula. Please keep it in mind. Okay. Now we all know a plus b to the 2. Everybody knows. This is a squared plus b squared, 2ab plus b squared. So this is a special case, a plus b to the n. If you know this formula for any n, you can write down the solution. Okay, so that's the most formula to learn binomial distribution. Now to learn binomial, let's first introduce a ballooning random variable. Now what is a ballooning experiment? A ballooning experiment. A ballooning experiment is a random experiment. First, it's random. The outcome is one of two mutually exclusive and exhaustive ways. Okay. So when you say a random experiment is a ballooning experiment, first, the outcome only have two options. Okay. For example, you flip a coin. It can be head or tail. Only these two options. Okay. You also can talk about success or failure. Only these two options. Female or male. There may be a third option, but we don't discuss it. Okay. Life or death. So these kind of experiments, we call it ballooning experiments. Okay, only two options. There is no third ways. Now, a ballooning trial, if you say a sequence of ballooning trials, okay, that just means you perform ballooning experiments independently. Independent ballooning experiments. Okay. So you flip your coin. You keep in mind, this is a sequence of ballooning trials. That means you independently flip your coin n times, for example. Now, for this ballooning trial, we can define a random variable, x. Now, think about what's definition of random variable is a mapping. Okay. Now, for each outcome, if it's a success, we say this random variable is 1. If it's a failure, the outcome, we say it's 0. Okay. So this x is called the ballooning random variable. This x only can be 1 or 0. Only two numbers. Okay. Now, so it's a discrete random variable. For this discrete random variable, so you can tell me what's a probability mass. If you know the mass, you know everything about this random variable. So probability mass, x equal to 1. That's denoted by p, for example. Since only have two options, probability x equal to 0 is 1 minus p. Okay. Sometimes we put these two formulas together. We define ballooning distribution. The PMF, so it's a discrete random variable, is given by this formula. Px is p to the x, 1 minus p, 1 minus x. What are the possible values? X can be 0, 1. You think about it. When x equal to 0, 1 minus p. When x equal to 1, p. So you just put these two together to give you a compact formula. So this is a PMF of a ballooning random variable. Once you know the PMF, we can calculate the mean, what happens to the variance of this random variable. Now, expected value of x. Only two numbers, 1 times p plus 0 times 1 minus p. So the mean of a ballooning random variable is just its success probability, p. Now variance, sigma square. Sigma square. So it's the expected value x squared minus mean square, p squared. X squared, 1 squared times p plus 0 squared times 1 minus p. So it's p minus p squared. So it's p 1 minus p. Okay. Now be careful, this p is a success probability. So p should be between 0 and 1. That's a success probability. So this variance is positive. Okay. So Bernoulli random variable mean is p. Variance is p, 1 minus p. The standard deviation. So it's sigma is square root p 1 minus p. So Bernoulli random variable is so simple. Okay, there is nothing to discuss more. Now, how to generate a binomial random variable from a Bernoulli random variable? Now, what is a binomial random variable? Just be careful. You need to remember this definition. That's very important. Okay. So you will perform a sequence of n binomial trials. Bernoulli trials. Okay. So you get a n independent Bernoulli random variables. That's a definition, Bernoulli trials. So you get x1 to xn. Okay. These are independent Bernoulli. Success probability is p. Okay. Since it's 0 or 1, so this is a n tuple of zeros and ones. Okay. So the final result, after you perform this n Bernoulli trials, for example, you're supposed to get 0, 1, 1, 0, 0, 1, 1, 0. Something like that. Okay. Now, what is your interest? We are interested in total number of successes. That's our interest. We would like to know how many ones in this sequence. Okay, how many ones in this sequence? Now, first, if you define a random variable, it's like how many ones. Okay. What are the possible values for this random variable? 0, 1, 2, to n. Don't forget 0. 0 means you have all zeros, no 1. Now, this guy is also a discrete random variable. So for the discrete random variable, you need to tell me what's a PMF. Probability x equal to lit x, for example. This lit x is one of these numbers. That means for this sequence, you have x ones. Okay. Now, what's the probability you have x ones? For this x ones, the probability is p to the x. So you have p, x p's. Now you have n minus x, zeros. So it's 1 minus p, n minus x. Okay. But that's not enough. The first job, you need to tell me which location you get ones. N choose x. So from these n positions, you first fix x positions. You said for this x position, I will put 1. For other n minus x positions, I get 0. Okay, so you have n choose x. So binomial PMF. Binomial PMF. Px is n choose x, p to the x, 1 minus p, n minus x. Support x from 0, 1 to n. That's a support. Now you may wonder why this is a valid PMF. Positive, no problem. Now the total probability, let's calculate. So this is the sum, x from 0 to n, n choose x, p to the x, 1 minus p, n minus x. Okay. So why this is 1? You will match this formula. We talked about that at the beginning of the class. Okay. If you compare these two formulas, you find out this A is P, B is 1 minus P. So this is equal to P plus 1 minus P to the n. It is 1. So this PMF, it is a valid PMF. Notation. Binomial distribution, we usually denote it by like this. B, N, P. Or sometimes you like a binomial NP. Okay. N, how many trials? P, success probability. What's the probability? You get 1. So this NP is called parameters. The parameters of the binomial distribution. If you would like to specify a binomial distribution, you need to tell me what's your n, what is your success probability p. For example, we want to say x is binomial 5, 1 over 3. If you use this notation, that means n equal to 5. P is 1 over 3. So the PMF is Px is 5 choose x, 1 over 3 to the x, 2 over 3 to the 5 minus x. Support x from 0, 1 to 5. Okay. Now, for a binomial random variable, what's the mean? What's the variance? Okay. So expected value of x. Definition. Summation x from 0 to n, x times n choose x, p to the x, 1 minus p, n minus x. I think we discussed a similar formula before. This is doable, but complicated. Expect variance, you get a second moment. this becomes difficult. Last time, I think my suggestion is don't try this at home. So based on definition, actually we face the difficulty. We cannot get the mean. We even cannot get the mean variance of a binomial random variable. Okay. There is a second way we can try. The second way we can try. So is we can use the MGF technique. MGF. From the MGF, we can get the moments easily by taking derivative. The moment generating function of a binomial random variable. Definition, e to the expected value e to the tx. X is a discrete random variable. So this is a sum. X from 0 to n e to the tx. N choose x. P to the x. 1 minus p n minus x. Okay. Looks similar, but in fact it's different. Now these two terms, you put them together. N choose x. P e to the t x. 1 minus p n minus x. Okay. Now you need to think about that a plus b to the power n again. This is your a. This is your b. So this is nothing but p e to the t plus 1 minus p to the n. Okay. We do get the formula. This is true for any t. This is true for any t. So after we get the moment generating function, everybody knows. By taking the derivatives, we can get the moments. Now let's take the first moment. Take the second moment. Okay. Let t equal to 0, we can get the mu. This is the first moment. NP. Now sigma square is the second moment minus mu square. Okay. So the mean of a binomial is NP. The variance of a binomial is NP, 1 minus P. That makes sense. What is P? Success probability. You flip your coin n times. What do you expect? How many heads? N times P. Okay. Now when n equal to 1, so that means you flip your coin 1 time. This just becomes a balloon. That's just balloon. There is another way you can get a better understanding of a balloon binomial random variable. Think about the definition. What's the definition of a binomial random variable? You flip your coin n times independently. You count how many ones. Okay, how many ones? That means what? You have x1, xn. These are the independent ballooning. Okay. So each ballooning is 0, 1, 0, 1, 0, 1. How many ones? You just take the sum. You just take the sum. This sum is just how many ones. If you get this new random variable, that's consistent with your definition. This guy must be binomial, sorry. Must be binomial. So binomial random variable is nothing but the sum of n independent ballooning. If you can realize this, the mean, the variance is straightforward. So x is x1 plus xn. Expected value of x. Expectation is linear. Expected value x1, expected value xn. Each one of xi's, they are ballooning. The mean is p. So p plus p plus p plus p. np. Now variance of a binomial, we said you need an independent. So there is no covariance part. So it's just the variance of x1, variance of xn. Each one ballooning, variance p1 minus p. So you have n p1 minus p. So this is another way. I think it's a better way. Think about what's a binomial random variable. It's the sum of n independent ballooning. Let's take a look at some examples. So x, this is the number of heads in n equal to 7 independent. Toss of a coin. Okay. So you're going to toss a fair coin 7 independent times. Then I define a random variable x. How many heads among these 7 times? So this x should follow a binomial random variable. So the n is 7. The success probability is half if it's a fair coin. Okay. The PMF is given by 7 choose x, half to the x, 1 minus half, 7 minus x. So this is 7 choose x, half to the 7. X support 0 to 7. Don't forget the support. Now the MGF for this guy. Okay. One minus p half plus p e to the t so this is 1 plus e to the t to the 7 2 to the 7. How many heads do you expect to see? Mu np 3.5 you will expect. That's the expected value. Okay. The variance sigma square np 1 minus p. This will be 4/7. Now probability. You can talk about probability. This random variable x is between 0 and 1. So what's the probability you will expect? 0 head or 1 head. So it's a discrete random variable. It's sum of the PMF at 0 and 1. You just plug in 0 and 1 here. You get 1/1/8 plus 7 1/8. So it's 8/128. So that's a probability you will get 0 or 1 head. If the MGF of x is okay. If you say for a random variable, the MGF is given by this specific formula. Since the MGF uniquely decides the distribution, this guy only can be binomial. 5/1/3. Okay. I have no requirement for you to memorize different MGFs. Maybe one exception is normal. For others, this binomial Poisson MGF, you don't need to memorize. So for this MGF, is binomial 5/1/3. The PMF this is the PMF. Now x can be 0, 1, 2, 5. We can get the mean. Mu is NP 5/3. Variance NP 1 minus p 10/9. So these two are the simple examples from the binomial distribution. We can take a look at a slightly more complicated example. In this example, it says let x1, x2, x3 to be independent. This is independent. 3 random variables. Okay. They have the same CDF. CDF the same, fx. So I define a y. What is y? Y is the middle value of x1, x2, x3. You think about, for these 3 random variables, independent have the same distribution. Any one of them can be the middle value. Okay. So y is the middle value of x1, x2, x3. The problem is asking you, what is the CDF of y? What's the CDF of y? So what's the distribution of y? Can you represent the distribution of y by the distribution of x? One thing you need to be careful. If you always choose the middle value, the distribution is changed. That's the bottom line. You need to be careful. You cannot say the y, since it's the middle value, is the same distribution. That's wrong. Okay. For example, you can think a more extreme case. I give you 3 numbers. You always choose the largest one. The distribution should change. Okay. So the distribution of y definitely is different with the distribution of x. Now what's the distribution of y? To understand the distribution of y, so you need to understand this event. Y less than or equal to little y. Okay. So you need to set up the connection. If the middle value less than or equal to a number, how to transfer this event to the origin x based on. So here I claim y less than or equal to little y. Little y is a number. If and only if at least two of the random variables x1, x2, x3 are less than or equal to y. Is this obvious? Or you need to think about it? Just straightforward? You think about the middle value less than or equal to y. Of course, at least the two of them less than or equal to y. Since y is the middle value, you don't know the largest one, but at least two should less than. Okay. If at least the two of them are less than or equal to y, of course the middle value should less than or equal to y. So this is straightforward comments. If and only if both directions are true. Okay. Now we can get the CDF of y. So this is the probability y less than or equal to y. Okay. So this is the probability at least the two of them, this x, less than or equal to y. So two situations that's related to binomial. Exact two. Exact two. So you need to choose which two? Three possible situations. They are less than or equal to y. So x1 less than y, x2 less than y, x3 should be greater than y. So if less than y, another one greater than y, this f is the distribution of x. So that's the exact two of them. Now all three of them are less than or equal to y. Okay. So that's probability x1. This is probability x1 less than or equal to y, x2 less than or equal to y, x3 less than or equal to y. All three of them should be less than or equal to y. Since they are independent, so you get this fy to the 3. Okay. So what do we have? The CDF of y, I represent CDF of y by the CDF of x. If x is a continuous random variable, you can take derivative, get the PDF of y. Okay. So this example is related to a statistic called order statistics. I think we will learn some of the order statistics at the end of this semester. Now, as you can see, the distribution is changed. It is different with the original fx. Okay, so that's a binomial distribution. Another related distribution is called negative binomial. Negative binomial distribution. Okay. Again, you're going to perform a sequence of Bernoulli trials. Okay. Now, for the binomial, you flip your coin n times. How many heads? That's binomial. Now, what is the negative binomial? This y is total number of failures before the auth success. Definition is important. Okay. So your experiments will end at the auth success. Now you just count how many failures before that. Okay. First, what are the possible values for this y? Support. Okay. So this is different with binomial. This y, total number of failures, it can be 0. That means your experiment is success, 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 all successes. You end. So that means 0 failures. 1, 2, 3. There is no bound. This can be infinity. Okay. For the binomial, you stop at n. Now the PMF. So this is a discrete random variable, PMF. Okay. You have a lot of 0, 1, 1, 0, 1. For these experiments, if you want to end the experiments, the last one, it must be success. Think about it. If the last one is not a success, you cannot end the experiment. Okay. This actually is auth success. Okay, the auth success. So before, you have R minus 1 successes plus this guy Y failures. So that's a pattern. Okay. Then you can discuss probability y equal to little y. For this y plus r minus 1 trials, you need to tell me which r minus 1 is success. So for these trials, you have p to the r minus 1. Now you have failure, 1 minus p to the r. But don't forget, the last one must be success. So for the negative binomial distribution, the PMF. Support. This is a negative binomial distribution. In the special case, when r equal to 1, r equal to 1, that means once you get a success, you stop the experiment. This y has a special name. It's called geometric distribution. Okay, geometric distribution. So for the geometric distribution is a PMF. Is p 1 minus p to the y. So this y can be 0, 1, 2. For this one, you can think about y is a valid PMF. You do the summation y from 0 to infinity, p 1 minus p to the y. This is a geometric series. For the general negative binomial distribution, why it is a valid PMF? You please think about it. It's not straightforward. Now let's take a look at one nice property of the binomial distribution. It says x1 to xm. These m random variables, they are independent. That's important, independent. Okay. Now what's the distribution? xi has a binomial nip. Okay. So for these m random variables, they have the same success probability, but they have different ni. Okay. Now, if I let y is a sum, then we claim the y also follows a binomial distribution. What is n? Sum of ni. Same success probability. Okay. If you remember what's the definition of binomial, that's so straightforward, this result. What is xi? I flip my coin ni times. How many heads? So what is x1? I'm going to flip my coin n1 times. How many heads? What is x2? I'm going to flip my coin n2 times. How many heads? Then the problem asks you, what's the distribution of y? That's just you flip a coin n1 plus n2 plus n3 plus nm times. How many heads? That's it. So intuitively, this is straightforward. If you really want to provide a proof, MGF technique. This is special for this chapter. You need to be careful. We will use this idea a lot. So we would like to show y follows a binomial distribution. The general idea, the MGF of y should be exactly the same MGF of that binomial. Okay. Now what is y? Y is the sum. This definition. Each step has its own reason. What is y? T sum xi. This is y. Okay. Next step, because they are independent. This is why independency is so important. Because they are independent, then you can have this. This is from chapter 2, independency. Okay. Each one of them is a binomial. We just calculate the binomial PMF. First one, since they have the same success probability, 1 minus p plus p e to the t to the n1. That's the first one. 1 minus p plus p to the et n2. 1 minus p plus p et nm. Now, if you want to combine these two formulas, P must be the same. They have the same success probability. Now you put them together. So we just showed the moment generating function of y, this sum, is given by this formula. This guy, it is the MGF of binomial then we can claim y follows this binomial distribution. So some assumptions independent, same P. Okay, so this is binomial distribution. Now we can generalize this binomial distribution to multinomial distribution. Okay. For the Ballooning trial, the outcome only you have two options, 0 or 1. Then you can think about why. Maybe you toss a die, you have 6 options. Okay. If the outcome has more than 2 options, then the random experiments become multinomial distribution. Okay. So the experiment results you have now you can generalize K mutually exclusive. And exhaustive ways. Okay. When k equal to 2, binomial. When k equal to 3, we call it trinomial. So for each experiment, you have k options. That's denoted by C1 to Ck. Okay. Pi, you have k options for each Ci. What's the probability? This is a probability that the outcome is from Ci. So the probability to get Ci. So I from 1 to k. Okay. You think about k equal to 2 for binomial distribution. Why we only have one p? Because one is p, another one is 1 minus p. So you only need to talk about one p. So this is P1, this is P2. Okay. Same thing. You perform these experiments n times. You just tell me how many from C1, how many outcomes from C2, how many outcomes from Ck. Okay. Now let x1 to xk. These are the non-negative integers. So that the sum is n. So you have x1 outcomes from C1, x2 outcomes C2, xk outcomes from Ck. But you only perform your experiments n times. The total sum should be n. So that's a constraint. Okay. PMF. Now, what is a multinomial random variable, xi? This is the number of outcomes from Ci. In fact, you define a random vector x1, x2 to xk. You run your experiments n independent times. You tell me how many outcomes from C1, how many outcomes from C2, from Ck. This is a discrete random vector, the PMF. This is a joint PMF. This is a joint PMF. So this is equal to n factorial, x1 factorial, x2 factorial to xk factorial. P1 to the x1, P2 x2, Pk xk. Okay. Support x1, xk non-negative, and x1 plus x2 plus xk is n. Okay. Now you may wonder what happened to this n factorial over these factorials. It's because of this. From n positions, you choose x1 positions, belongs to C1. From n minus x1 positions, you choose x2 positions, belongs to C2. You do this again and again. This will give you n factorial, x1 factorial to xk factorial. Now my first question, can you tell me this x1 to xk, are they independent? Can you tell me, are they independent or not? Independent or dependent? Huh? Huh?
Dependent.
Why is that?
I think because of the support.
Okay. So a row we can separate. Unfortunately, this support destroys everything. Okay. This support is not like a rectangle shape. It's more like a triangle shape. So x1 to xk, they are dependent. Or you can think about the case we just mentioned, k equal to 2. K equal to 2 binomial. Binomial. Okay. Now if we use the multinomial notation, that means what? x1 is how many belongs to C1. x2 is how many belongs to C2. Now what's the relationship between x1 and x2? If you know x1, you know exactly what is x2. This is why in binomial we only introduce one x. They have the perfect linear relationship. For these two, the correlation coefficient is -1. They're perfectly correlated. Of course, they are dependent. Okay, they're dependent. So this is binomial distribution. Now we can talk about trinomial. Trinomial distribution. That means k equal to 3. This way. Okay. So x1, x2, x3. If you know x1, x2, x3, you know is n minus x1 minus x2. So for trinomial distribution, you only need to define 2 random variables. For example, let x equal x1, y equal x2, then x3 you know automatically. You don't need to know. You don't need to define x3. Okay. So we say x and y have a trinomial distribution. If the PMF is given by this formula, so p x to y n factorial x factorial y factorial n minus x minus y factorial p1 to the x, p2 to the y. Here is 1 minus p1 minus p2, so it's p3, n minus x minus y. Okay. Now support x and y should be non-negative. Also, x plus y should lessen or equal to n. P1, P2 success probabilities. P1 plus P2 should less than 1. The success probabilities plus P3 is 1. So for trinomial distribution, it is a bivariate random vector. Bivariate distribution, we learned it from chapter 2. They are dependent, this x and y. The MGF, now we have two arguments, T1, T2. The definition, expected value T1x plus T2y. You calculate the sum, you can get this formula. If you let T2 equal to 0, if you let T1 equal to 0, look at the definition. T2 equal to 0, this part disappeared. That's the MGF of x. T1 equal to 0, this part disappeared. That's the MGF of y. These MGFs look very familiar. X binomial, y binomial. So x and y, you put them together, is called trinomial distribution. Interestingly, the marginal distribution of x, y, they follow binomial distribution with success probability P1, P2. Now the conditional distribution, y given x. So this is a conditional distribution. We know the joint, we know the marginal. We can get the conditional distribution. So it is a ratio. The numerator is a joint distribution. The denominator is the marginal distribution of x. It's a binomial. It's a binomial. if you simplify this formula, you can realize the conditional distribution of y given x is given by this formula. So y given x is again binomial. Okay. I hope you can feel the beauty of multinomial distribution. The joint multinomial, marginally binomial, conditional binomial. So y given x binomial. So expected value binomial we know. So this conditional expectation. Okay. Of course, the x given y is also binomial. Okay. The conditional expectation of x given y, just n minus y, p1, 1 minus p2. Okay. The correlation coefficient, I'll skip the details, is given by this formula. So it's negatively correlated. That makes sense. If one is getting larger numbers, another one will get less numbers. So it's negatively correlated. Okay. Now let's end this with an example. X, the number of times that an even number comes up in 30 rows of a die. Y is the number of times that the result is 5. Okay. Now if x, you observed x equal to 12. What is the expected value of y? Okay. So in this example, first, what's a random experiment? I'm going to roll a die 30 times. What's x? How many even numbers? What is y? How many 5s? You get 5. Okay. So this problem said, after my experiments, I find out x equal to 12. The 12 even numbers comes up. Ask you what's the expected value of y. So this is a conditional expectation problem. Can anybody tell me the answer without any calculation. What is y? What is the expected value for y? What is the expected numbers? You get 5. Huh? Is it 6? Is it 6? Why is 6?
Because there's 18 odd numbers that come up, and there are 3 options for odd numbers.
Okay, that's a good intuition. So the answer is 6. That's it. Why is 6? Now let's use our intuition. Okay. So you roll your dice 30 times. Even numbers 12. So you have 18 odd numbers. 18 odd numbers. 1, 3, 5. 1, 3, 5, same chance. 18 divided by 3, 6. The answer is 6. Now mathematically, y is 6. So this is a trinomial distribution. Trinomial distribution means your outcome 3 possible situations. Which 3? 2, 4, 6, 5, 1, 3. Even numbers 5, 1, 3. You roll a die, you have 6 options. Now my interest, these 3 options. Okay. P1, half. You have chance, you get an even number. P2, 1 over 6. You have 1 over 6 chance, you get 5. P3, 2 over 6, 1 over 3. Okay. Now for the trinomial distribution, this is x. This is y. Okay. So this x and y follows a trinomial. N is 30. N is 30. Okay. So P1, half. P2, 1 over 6. Y given x. Y given x. We just mentioned is also binomial. Y given x is binomial 30 minus x, 1 over 3. So expected value of y given x is 30 minus x, 1 over 3. This is a mathematic derivation, okay? But say consistent with our intuition. If x equal to 12, you have 30 minus 12 over 3, it is 6. So you expect to say 6 5s if you know x equal to 12. Okay, that's all for today.